All right, now we're going to start the freefall motion section of the kinematics review. One thing to remember with freefall motion is that for every single problem, if it goes up, if it goes down, doesn't matter. The acceleration is negative 9.8 meters per second squared because each one of these objects is in midair, not getting pushed or pulled by anything other than the gravity of the Earth. Number 15, a stone falls freely from rest for 6 seconds. And since it starts from rest, initial speed is 0. How fast is the stone going when it strikes the ground? VF is the question mark. Now, sometimes people want to say, oh, when it hits the ground, it stops moving. Yes, I know after it hits the ground and comes to a stop, it will stop moving. The question is asking, how fast is it going as it hits the ground? That instantaneous moment just before it hits the ground. And that's what we're looking for. How fast is it going at that moment, not after it's already hit and stopped. So we're going to pick the equation that does not have d in it, which is Vf equals V naught plus AT. It's already set up for the thing we're looking for, so you just plug in our numbers. 0 plus 9.8 meters per second squared, don't forget that's negative, times 6 seconds. And that gives us a final velocity of negative downward 58.8 meters per second. Number 16, you throw a ball straight up into the air with a velocity of 13 meters per second. That's our initial speed. What is the maximum height of the ball and how long does it take to get there? At the maximum height, the final velocity is 0 because it has to stop on its way up before it can come back down. And acceleration, as always, negative 9.8 meters per second squared. We're solving for both the displacement and the time. We're going to solve for displacement first. So we're going to use the equation that does not have time. That's Vf squared equals V naught squared plus 2AD. Solving for d, we're going to move the V naught squared over to the left side first, giving us Vf squared minus V naught squared. We're going to divide by the 2a, so that's why it's in the denominator, and plug in our numbers. 0 meters per second squared is just nothing, minus 13 meters per second squared divided by 2 times negative 9.8. The negative in the denominator and this negative in the numerator cancels out, giving us a d displacement of 8.62 meters upward because it's positive. Now we're going to solve for time. How long did it take to get there? I'm going to use the equation that did not have d in it in case you solve for this first, or just in case we made a mistake here. We didn't, but you never know. Vf equals V naught plus AT. We're going to solve for the time, so we're going to move V naught over to the left first. Vf minus V naught all over A equals time. Plugging in our numbers, 0 minus 13 meters per second all over negative 9.8 meters per second squared equals time, and that's 1.3 seconds. Number 17. A physics student launches a bottle rocket into the air with an initial speed of 24 meters per second. So that's our initial. How long does it take for the rocket to land back on the ground? Well, the d, when it gets back to the ground, is 0. It started on the ground, it gets back to the ground, so the total displacement is nothing. I know it went up and it came back down. Remember, displacement is how far it is from where it started. The equation knows what it's doing. You don't need to know how high it went in this problem. The displacement is 0. One thing which does happen when you launch something up in the air or throw it up in the air, if it gets back to the same height when d is 0, the final speed is going to be the same as the initial speed, but velocity-wise, it's downward, so it's negative. The initial velocity is upward 24 meters per second. The final velocity is downward 24 meters per second. And the acceleration is negative 9.8 meters per second squared. In case you didn't realize that the VF was negative 24 meters per second, I'm going to use the version of this kinematics equation that has the quadratic. D equals V naught T plus 1/2 AT squared. We talked about where this came from in a previous problem. And time is negative V naught plus or minus the square root of V naught squared plus 2AD all over A, plugging in our numbers. Negative 24 meters per second plus or minus the square root of 24 meters per second, squaring it, plus 2 times negative 9.8 meters per second squared times 0. This whole term goes away. And that's going to be divided by negative 9.8 meters per second squared, and we get a time of 4.9 seconds. Number 18. While standing on a bridge, a student throws a rock up into the air. It takes a rock 3.8 seconds to hit the water, so that's our time, and that water is 32 meters below, so make sure since it's below, it's negative 32 meters. It's 32 meters lower than where you threw it, not 32 meters higher. With what initial velocity did the student throw the rock? We're looking for v naught. We're going to use the equation that does not have vf in it. That's going to be d equals v naught t plus 1/2 at squared. We're solving for v naught. So we're going to move the 1/2 at squared over to the left by subtracting it, giving us d minus 1/2 at squared divided by time. That's going to give us the initial velocity. Plugging our numbers in, negative 32 meters minus 1/2 times negative 9.8 meters per second squared times 3.8 seconds, square that, all divided by 3.8 seconds. The 3.8 in the bottom and this 3.8 do not cancel because there's two terms here. So don't start trying to get ahead of yourself. Plug the whole thing into the calculator and you get an initial velocity of 10.2 meters per second.